Good afternoon. It is 2:48 p.m., February 19th, 2023, and these are the Tobin Time Travel Talks. Today we're going to start going over all the background science you'll need to know in order to understand time travel. And just to be safe, we're going to go way back down to the basics. So today we're going to talk about time and infinity. Because it would be colossally unfair to talk about traveling through time without first talking about what time is. So to that effect, what is time? Time is a measure of how far apart things are, but not in terms of space. So instead of measuring distance, it's a measure of duration. And more fundamentally, time is a dimension. So like when you're looking at this screen here, it has height and width, which we could also call X and Y. And of course, when we're walking around the real world, there's a third dimension, which we can call Z on the screen. We look at space as three-dimensional, and time complements it as a fourth dimension. It shares some similarities to those spatial dimensions, but is different in some very essential ways. But trying to portray four dimensions graphically on a two-dimensional screen is very difficult and not very practical. So usually we'll just have like an X and a T, or if we're feeling really fancy, we'll have X, Y, and T. We'll just replace the Z with the T. For a long time, people would look at time as being a construct, something that's inconsistently experienced from one person to the other. But Einstein's theory of relativity kind of smashed that and inextricably tied time and space together, giving it an incontrovertible meaning. Time is real, and it is observable. We'll talk about relativity a little bit later. Except there's this one thing I want to talk about right now that's going to be helpful for us, and that's the concept of space-time. So ordinarily, you need three numbers to describe something's location in space. It's X, Y, and Z. And you need one number to describe its point in time. But since time travel supposes that you can move through time in the same way that you can move through space, it's helpful to look at them as the same thing. So we can combine space and time, three numbers and one number, into a single four-number thing called space-time. Right? So now instead of referring to a point in space and time, it's a point in space-time, or a space-time location. And going forward, we're going to call the exact configuration of things at a single spacetime location an event, and the sum of all points and events of spacetime is the spacetime continuum, or the fabric of spacetime. There's a funny quirk about physics in that the laws are symmetric about time. In other words, if you observe any given phenomenon, it would look equally valid if you saw it moving forward in time versus if you saw it moving backward in time. For example, if we saw a ball flying through the air in a ballistic trajectory and we played that flight backwards, both would look like valid versions of the events. In that case, how do we know what direction time is actually flowing? I mean, we can't exactly rely on our own senses because, for all we know, we might be flowing backwards in time too. The main way we know which direction time is flowing is because of entropy. Entropy is usually described as the amount of disorder in a system. For example, a messy room has more entropy than a clean room. But more precisely, entropy is a measure of how many ways you can rearrange something without fundamentally changing what it is. For example, let's put two particles in a box with a partition. So they can be on either the left side or the right side. We don't care if they're at the top or bottom, or precisely where in each side they are, just whether they're on the right or the left. If there's one on the left and one on the right, they can swap places without the system changing. If I swap them, there's still one on the left and one on the right. So there are two identical ways to have one on either side. Meanwhile, there's only one way to have both of them on the right, and only one way to have both of them on the left. Since there's more ways to rearrange the first system, it has higher entropy. When we increase the number of particles, the math gets more complicated, but the outcome is pretty similar. Let's up it to 4 balls, and we'll color them to make it a little bit clearer what's happening. With 4 of them, there's only one way for all of them to be on the right, and only one way for them to all be on the left. But if we put 3 on the right and 1 on the left, there's 4 different ways to rearrange it. Each ball gets its own turn on the left. And by the same logic, there's 4 ways to have 1 on the right. But if it's 2 on each side, there's actually 6 configurations. I did that really quick, so let's replay it and list them all out. By now you should be starting to see a pattern. You see, no matter how many particles there are, there's higher entropy when they evenly distribute themselves throughout the space. Or more generally, we get higher entropy when all of the components of a system just spread out as much as possible, because at that point you get more ways to swap them without changing the system. That's why a messy room has higher entropy than a clean room. How about we look at a slightly less artificial example, one you might have seen before. Let's take a glass of cartoon water and drop some food dye in it. In this glass we have 2 basic kinds of particles, red food dye and water. And at the moment the food dye is dropped in, all the dye particles are inside just this tiny little drop. You can only swap them around in this little bitty space. We can swap them here and here, but we can't swap them here and here, so we have low entropy. If we look a few moments later, the food dye starts to diffuse, and it fills a larger volume, and the water starts to take up the same space. There's more ways to swap particles because they take up a larger volume. So our entropy is actually higher now. And if we wait for full diffusion, well, the dye and the water take up the whole cup. You could swap 2 particles from anywhere across the glass. We can swap here and here, or here and here, or here and here. So this is maximum entropy. You'll notice the entropy of that system increased over time, and in fact, that's the second law of thermodynamics. The entropy of a closed system can never decrease. And what makes the system closed is that we never interfere with it. Nothing touches this glass once the drop has gone into it. Okay, now you might remember the whole point of this digression on entropy is because we wanted to know which direction time flows, and now we have our answer. Because entropy can only increase with time in a closed system, whichever direction has entropy increasing, that's the direction that time is flowing. So remember this ball that was flying back and forth? We don't know which way is forward and back until we see which direction has more entropy. So maybe we zoom out and see that, oh, on one side, the ball is inside a cannon. Obviously, this is the start, and shooting it out, that's the end, right? Well, don't forget, our perception might be running backward in time, so just because we see the ball leave the cannon doesn't mean that that's necessarily the beginning. We gotta look at this analytically. So how exactly do we compare entropy at the beginning versus at the end? I mean, there's a lot of little things we could look at, like the heat conditions of the air, but that analysis is kind of a slog. The easiest thing for us to look at is going to be the gunpowder. You see, at one end, the gunpowder is, well, it's a compact powder, and at the other, that gunpowder is in a large, hot gas with a bunch of extra chemicals in it. When you light up the gunpowder, it wants to turn into a gas and expand, pushing out the ball before it expands out into the environment. So there we go. We start out at low entropy, then the gunpowder expands, increasing its entropy. Time moves in the direction where the ball leaves the cannon. All right, that gratuitous digression is complete. I just wanted to make sure we cover all our bases so that there's very few questions remaining. That's right, I am willing to sacrifice viewer engagement for technical completeness. Maybe not the best business decision. Okay, moving on. Have you heard of timelines? They're kind of super important to time travel. Throughout these lectures, we are going to use the term timeline to refer to all of the events of a single universe, or all of its space-time, from the beginning of time to its end. A timeline refers to a specific series of events. So if one series of events contradicts a different series of events in even the slightest way, they must be different timelines. For example, if in one series of events, Matt goes to the park for his 20th birthday, and in a different series of events, Matt stays home for his 20th birthday, they must be different timelines. Okay, you've probably seen timelines diagrammed before. We have a line, and we have events, and because we read English from left to right, these events progress from left to right. Here we've diagrammed a timeline of the life of Tim Travers. We're going to be seeing a lot of Tim. Now, since I started writing this, a movie has been announced called Tim Travers and the Time Traveler's Paradox. This is completely unrelated to that, and in fact, I believe I came up with the name first. Not that using the name Tim Travers to describe a time traveler is an act of supreme creativity. And in fact, Futurama beat us both to the punch in 2012 with the time traveler Chris Travers.
I was sent back from the year 3028 to prevent Nixon from getting elected.
Okay, moving back to our timeline, you'll notice this isn't drawn to scale. If it was, it would look like this. But that kind of clutters it up, and it doesn't really enhance the information, and if I worry about the scale, it's going to take forever to draw these things. And in the long term, the scale isn't as important as the order, so just run with it. Now, obviously this diagram simplifies and stands in for a lot of events that aren't being shown. In fact, we could take some events off this diagram to simplify it. Or we could expand it and show more events. Even these year markers could correspond to any number of dates in the given year. In this case, since Tim's actual birthday is September 3rd, the 1989 marker is actually located at September 3rd, 1989. Or 1989.67 if we want to go by fractional progress through the year. Kind of reads like a Star Trek-style stardate, doesn't it? But again, the specifics only matter if they relate to other events. So we'll just stick with 1989 for now. The point is, there's not just one single way to show a timeline. They're a really flexible way to show how events relate to each other. And I hope you like them, because we're going to have just so many timeline diagrams, and they're going to get wacky. Alright, now that you know what time is, let's talk about infinity. The term infinity refers to just an unendingly large amount. It's beyond what we would call any number. And whether we treat it as a number or not is usually a matter of semantics, even though it's technically just a concept. In order to talk about practical infinities, we have to talk about discrete values, continuous values, and spectra. Discrete values are ones that can be individually counted. You can't have half of a discrete value. For example, there are 39 letters in this sentence. Those letters are counted discretely. Or like you could have 5 people in your meeting. You can't have 38 and a half letters or 15 and 3/4 people. Not counting offensive jokes and political policies. In contrast, a continuum includes all the decimals, fractions, and other numbers in between the whole numbers. Distance is a continuum, as you might have been able to infer from the phrase space-time continuum. You can have 5 meters, 3.2 centimeters, 1.5 miles, or like pi feet. Notably, no matter how good you ever get at measuring, you'll never be able to measure an exact amount in a continuum. You can get arbitrarily close, but there's always going to be some level of error. If you want to cut a piece of wood to exactly 1 meter, and let's say you have a really amazing ruler and equipment, you might be able to cut it to, say, 1.000 meters, right down to the millimeter. But then if you get out a micrometer, you might find you actually sliced it to about 1.0002 meters. If you have top-of-the-line tools, maybe you could get as close as a micron, 1.000000 meters. And still you might be off by nanometers, 1.0000009. It's a very good cut, but by definition, it is not exactly 1 meter. Yeah, I know that looks like a lot of zeros, but in decimals, there's always more zeros. Or, to put it another way, there are an infinite number of numbers between 0.9 and 1.1. You got 0.91, 0.99, 1.01, 1.001, 1.0001, etc. You can always, 1.05, you can always come up with another number just by adding another digit somewhere after the decimal. And since there are an infinite number of numbers, the chances of hitting the exact one you want, in this case 1.0, that chance becomes 1 in infinity, which is the same as 0. Technically, the correct way to phrase this is with limits and calculus. Precision is always a range, and practically speaking, when we say exact with some continuous value, we're talking about some small range of tolerance. Okay, time for another tangent. So, to be clear, the word precision refers to how small our measured error is. This number is more precise than this one because we measured it down to the nanometer, and that one is only to the micron. Accuracy, on the other hand, is about how close to the actual value we are. So if we're aiming for 1.0, this number is more accurate because it's closer to 1. But this number is more precise because we have more decimal places on it. Moving on to spectrum. A spectrum is a continuum where some associated value changes along the way. The most obvious example is color. Visible light ranges from about 400 to 780 nanometers continuously. The actual color of the light changes along with the wavelength. So color is a spectrum based on the wavelength continuum of electromagnetic radiation. The concept of infinity is important to time travel because time is a continuum. No, we're not going to talk about Planck time here. But what's important is there are an infinite number of points in time between any two other points in time. And therefore, there are an infinite number of points of time travel to pick from. Okay, that's it for time and infinity. Next time we're going to talk about perhaps the most misunderstood concept in time travel, chaos. That is, the butterfly effect. If you want to support the series, or if you're ready to dive into the nitty-gritty of time travel, consider purchasing the Chronoversal Compendium on Amazon, or follow the Ingram Spark link in the description for a special discount on the hardcover. There's also some Chronarch Butterfly merch available on TeePublic and Redbubble. That's all for now. See you yesterday.